Today we want to learn how to get most out of our NCEES approved calculator, the strongest one being this guy, TI-36X Pro. And it has a lot of useful tools. It has a big screen which helps you to avoid writing things in a straight line format. Very possible for making mistakes that way. But now I want to show you with these features like this fraction and this power display tools how you can actually type the exact equations in your calculator instead of converting it to string lines with many parentheses and then make mistakes. So let's say we want to solve 3 over let's do 2 5 7 here, and then another fraction 5 plus sine 40 and so on and so forth. Or you can even add another thing here. It's a power of 7. You have tangent 20 degrees. So of course, if you want to use the traditional format, enter the whole thing as one line with parentheses, you need many of them. Or if you want to do step-by-step solving, then and divide and continue, then it will be out of the time for your PE exam and your actual professional calculation where you need to deliver tons of calculations every day. So here all you need to do is just press and then use the fraction button here. It goes you to the below, so you put 2 here plus 7 and another fraction sign. Don't forget, for the top you need to power it with this guy to tangent 20, and for the bottom you need to do 5 plus sine 40. So this way it's exactly the way I have it on the paper, so I can check things very quick and then I can press enter. So this is done, and it's very unlikely that you make mistake or miss anything with this approach. And to link it to our water resources and hydraulic type of calculations, now I want to show you how to solve stuff for an open channel. We have an open channel here, trapezoidal open channel, and we have bottom width 10, 2 to 1 for the side slope. We have Q 30 cubic meter per second, and side longitudinal slope of 0.001, and a concrete channel with roughness coefficient of 0.013. So this is set, and we know that we need to use Manning's equation for finding the normal depth, right? We want to solve for normal depth, which cannot be done explicitly in this way because now we have the depth unknown. But we just set things up. The general format: cross-sectional area times hydraulic radius to 2/3 should be equal to NQ over S to half. And this right side is known. We have N, we have S, and we have Q. So if we do this for this problem, it's gonna be 1233. And I skipped the basic calculations because I want to show you how to solve an implicit equation using this calculator. So now setting this left side makes it like we have 10 plus 2y as the area times by y. That's my area, and for my hydraulic radius I have 10 plus 2y times y over 10 plus 2y radical 5, that comes from the z part, and to 2/3, but calculator friendly version of it is 0.67. This should equal to 12.33. So now we want to solve this. We have y sub n unknown in several occasions. Y sub n, y sub n, y sub n, y sub n, and y sub. So we have 5 cases of y sub n in the left side. It's trapezoidal. Of course, among the geometrical methods and shapes like rectangular and triangular, this one has the most complex form. But with this calculator, you don't need to worry. Now we have another helpful tool here. It's called Numerical Solver with the blue. So if I press second and if I go to Numerical Solver, then I can set it up for first I erase what I have from the past, and then I just type this in and have it solving it for me. So this is 1 and 2 parentheses 10 plus 2. I press X, it doesn't matter how you present. You have all options, but X is just the first time you press this key. So just solve it for X instead of Y, that's the same thing. Times X goes, and then now we need to multiply it with the bigger term here. We have hydraulic radius. Then now I'm going to use my fraction so I don't mess things up. Then I have on top 10 plus 2x times x, and on the bottom I have 10 plus 2x times radical 5. So I have this times x, and then I can close this. I should power it with this tool that I showed you before. Power it to 0.67. No need to use the hat version of the power previous generation of calculators. Now everything should show in the right way that you have it, so you can quickly check. And we go to the other side, we put 12.33. So now you can enter and then solve for what it recognizes that you have x as an unknown, so you can solve. It is like all other trial and error that you use, even the manual one, you always start with an initial guess. That's also for this numerical solver, and you need to be smart a little bit, not really too smart to know the final answer in advance, but just have some sense of what you're solving for. So if this is my domain, then I'm solving for x here, and this is like this whole function should equal to the root of this. So if I call this part with red, let's say I want to call it like f1, so you have a function f2, let's call it f1 minus 12.33, this is minus. You want to set this to 0, right? This is you're setting this f2 to 0. You want to have f1 equal to 12.33, so I want to call it this f2, meaning that if I want to show you f2 here, then this equation probably has multiple roots, right? It has a form of this and stuff. So we all know that what we're solving for depth is a positive thing. So this is a positive number. And this equation might have other roots in the negative side. We don't want them. We only want the number that makes sense for this. You're solving for depth of a trapezoidal channel with this geometry, so it makes sense that it's somewhere between like 0.1 meter to like 5 or 6 meters. we shouldn't start with 17,075 as the initial guess. That's a very bad initial guess. And also never use zero. Never use zero because it messes your algorithm up. So if I put zero or huge numbers like this or negative numbers, it's just a very bad initial guess. It might take 10 minutes for my calculator to find it, or it might find some useless answers. So I just put something, always is a good guess. You can have one, or for this type of calculation, 1, 2, 3, whatever makes sense for your actual initial guess. And then you do this, and then you press solve. So you see a very little sand clock button here, and it's solving. It should take like 30 to 40 seconds because it's doing the iterations, and you can see it's actually done. So we have it as exact number. This left minus right is equal to 0 means that we don't have a range of uncertainties. Left and right guesses are exactly equal. So you can see the final answer is calculated as, let me change my marker, x, or basically my y-n equals to 1.089. Okay, now I want to show you another useful tool in this NCEES Approved Calculator called Polynomial Solver. Numerical Solver is the one that we used for finding a normal depth. It was an implicit equation. We didn't know the form of the equation, so we just tried to solve it iteratively with this tool. But for the polynomial solver, that's when you actually know this is your second or third degree equation. So you can solve for all the roots of the equations at once, all of which being meaningful for your problem. So here I have a rectangular channel. In the supercritical form, I have the depth as 0.15 meters. I want to find the alternate depth in this system given the 0.2 cubic meter per second discharge rate. So we use the specific energy equation here, being E equals to y plus q squared over 2ga squared. And because we have this for the supercritical mode, so we find the specific energy in that situation being 1.5 plus q squared over 2g area squared. And area is nothing but 0.4 times 0.15 squared for the whole thing. So this equals to 0.716 meters of specific energy. And now I need to set this again and find the roots of the cubic equation for the alternate depth. Basically now I have 0.716 equals to y, which is unknown for now for this system, so that's why we're solving. Plus again q to 2g, and instead of a we can put area, right? We can say bottom width squared times depth squared, and this is the same depth that we're solving for. So after simplification we get to 0.716 equals to y plus 0.01274 over y2. And if I want to form it to the standard shape, then my cubic equation which is a polynomial equation, is y2 minus 0.716 times y2 plus, it's best that you show all the term. There is no term for first degree, so I show 0 times y plus 0.01274 equals to 0. So now we want to solve this and find the alternate depth. Turn on the calculator, go to this polynomial solver, shift pol solver. It can solve the second degree or third degree, so I put number 2 to go to the third degree. So these are the coefficients. My coefficient number 1, I have 1, so I clear this and press 1, enter. For b, I have minus. Be very careful about the signs. I have minus 716. For c, be sure you do this right. That's 0. And lastly, I have this. So check everything and then enter for solve. So you can solve it. It gives you all the roots. So for depth, you have 0.69. If you go down, you have 0.15, and if you go down, you have a negative number, which is useless, all in meters. So this is not the answer. This is actually what we started with. So it's our depth at the supercritical. And this thing that I'm gonna box it a lot is my final answer for this situation. So in this system, the depth of the subcritical flow is 0.69 meters. And that's how we use our calculators to get the most out of it in the limited time for the PE exam, and also to solve hydraulic problems.